Hello and welcome to this next lecture in Purification and Separation methodologies. In today's lecture, we will study about a very important chromatographic method, which is gas chromatography. In this method, we will learn about the details of the instrument, which is gas chromatographic instrument. We would find out about the columns which are used in this method, the sampling, injection modes, and finally the detectors used in this important methodology. Here on your screen you could see an image of a gas chromatographic instrument. Let me define this gas chromatography for you, and then we will try to learn through the definition about the technique. So, this is an advanced technique which separates a complex mixture of volatile chemical substances in short time based on their distribution between mobile phase and stationary phase. Now, there are certain very important key terms which I would like to draw your attention towards. The first term is it's an advanced methodology. So, it's a better method than what we have learned so far about TLCs and glass chromatography and this paper chromatography. It's a better one than that. It's better because it is able to separate many more number of solutes than what could be achieved in all those methods. And then finally, it is also able to do that in a very short time, which could just range from some minutes to, let's say, 1 hour or so. Now, that's something very remarkable, because there are two very contrasting things we are saying. On one hand, we are saying we have a mixture of let's say n number of components, let's say 100 components, right? And on the other hand, we are saying that this method is able to resolve all those 100 components within just minutes, or let's say an hour of a chromatographic run. What that means? That means we need to now evolve certain specific columns which would have a large number of theoretical plates. As you could recall from what we have learned from Van der Merwe equation and other plate equations about resolution, we know that more is the number of theoretical plates, more would be the resolution of peaks, and more would be the number of components which could be isolated in a small time. Now, that's something very unique, and we will now see how we are able to do all that and achieve this type of complex separation in short times. This is a schematic diagram of gas chromatographic instrument. Now, as the name implies, it's gas chromatography. It means the mobile phase used in this method is a gas. So, you would use a cylinders of gas which would be used as mobile phase, and this mobile phase would then be carried on to a injector port, which is here shown on red block, which then carries through to this large spirally wound column, and both this injector port and the column are kept inside a GC oven, which means they are kept inside very high temperatures, which range from let's say a few, let's say 100 degrees Celsius up to anywhere around 400 degrees Celsius, depending upon the solute. Then it merges into this detector, which is this blue block. From this detector, the solute would go down to this waste, and a recorded chromatogram would provide you the measurement of what you have attained out of this chromatographic experiment. Now, in this gas chromatography, as one would establish that the gas is a mobile phase, most commonly used gases are all those inert gases, it could be helium, it could be argon, or it could be nitrogen. Most generally, the gases we use is helium and argon. We also sometimes use hydrogen as a mobile phase in gas chromatography. Now, all these gases provide chemical inertness towards both the sample and the stationary phase. They do not interact with either the sample or the stationary phase. Also, in gas chromatography, your stationary phase is the main factor which determines selectivity. Now, that is very important because what we have seen so far is I told you there were three important pillars as far as chromatographic separation was concerned, and mobile phase constituted one of those pillars. But in gas chromatography, since you are using a gas as a mobile phase which is inert, would not react, and hence it really does not contribute much to chromatographic resolution or separation of a mixture. So, then mostly it relies on the kind of stationary phase, and stationary phase plays therefore a very important role in gas chromatography. So, then selection of stationary phase is also equally important, and it is generally determined by solutes, the kind of boiling point solutes would have, because the separation would be governed by different boiling points of the solutes. Nevertheless, the solutes interaction, their adsorption, their partition into stationary phase would also be a factor, but then their boiling point is a very important factor for resolution and their separation. And secondly is solutes interaction with the stationary phase. So, then solutes, as I said, with different boiling points can be easily separated. Now, if they have very significantly different boiling points, separation in gas chromatography is easy. But what if the solutes you are taking are not so easily resolved and do not have much difference in boiling points? So, we will see what would be the implications then. Now, the columns or the stationary phase used in gas chromatography can influence, first of all, or its choice can be influenced by the amount of sample which it needs to handle. Then also the separation efficiency, different columns of stationary phases would have different efficiencies. Then the amount of time which would be required for separation also would determine what kind of stationary phase one can use, and then the number of solutes which can be easily separated. So, that can also be taken up when a choice of stationary phase is to be made. One very important thing which I have not spoken so far, and that is actually the one of the basic fundamentals of gas chromatography, is the solute which you are going to take must be volatile, and within the column it should remain in a vapor phase, so that it travels effortlessly inside the gas phase. Right. So, any solutes which are not mobile, which are not volatile, can be a problem. The types of gas chromatographic columns are basically two types of columns used in GC. One is this packed columns, and the other ones are called capillary columns or open tubular columns. Now, as the name implies, the packed columns would contain some particulate packing material, right, which could have those silicas or diatomaceous earth bonded with some liquid stationary phase or so. The outer column is made up of either glass or stainless steel or copper or aluminum. Generally, packed columns are not too lengthy, they are up to 5 to 6 meters in length, and their internal diameter is about 2 to 4 mm. So, their internal diameter is also a bit on the higher side. Now, this is one image where you could see one such packed column. So, in this column one could see the solid support, and as I said, solid support could be diatomaceous earth, or it could sometimes be glass beads, which had been a recent addition to kind of solid support one could have. And then this solid support, as you could see, is coated with a thin film of stationary phase. This part of bonding it with a stationary phase or thin films of stationary phase we have already seen, right. Now, As far as capillary columns are concerned, they are open tubular. It means they are not packed. The internal diameter, the internal of the side of the column is empty. It does not contain any packing material. They are of great lengths. They could be up to around 100 to 150 meters in length, and their internal diameter is generally way smaller than what we saw in the previous case. So, by having so much of length up to 100 to 150 meters, one could easily see that their number of plates would be enormous. And at this point, I can tell you that having up to, let us say, 1 lakh or more than 1 lakh number of theoretical plates in one capillary column is also not very uncommon. So, then it also tells you about how we are able to separate a complex mixture when we are having these many number of theoretical plates. If you compare it with a normal column, I think having just a few thousand number of plates is also is on the higher side. Generally, these capillary columns comprise of 3 layers. The outer layer is a polymer coating. It could be a polyimide coating or so. Internal to this is fused silica, which could be those diatomaceous earth particles, and then to which to this fused silica are bound the stationary phase, which could be a solid, very thin film. Thinner is the film, better is going to be the resolution. And again, whenever I am saying all these things, you must keep in mind the kind of theories and the kind of equations we have already derived in past. One of them, a very important one, was Van de Meter equation, and you could see when I say thin films, it means that I am talking about very small c. You remember that there were those 3 factors A, B and C. So, it minimizes C, and minimizing C means you would have a large number of theoretical plates. Now, in these capillary columns, they could again be of 2 types. They could be of wall coated open tubular type, in which the stationary phase is coated on the column's wall, and they could be supported coated open tubular SCOT, in which the stationary phase is coated on solid support which is attached to the column's wall. So, here you could see there is this one SCOT column here and WCOT, in which the stationary phase is directly coated to the walls is shown here. Now, what are the advantages and disadvantages of both these kinds of columns? So, you could also see for yourself. I told you the packed columns, they have high diameters. So, then having high diameters means that their sample loading capacity is going to be more, right. So, you could also use them for preparative purposes, though a use of GC column for preparative purposes is not so common. Capillary columns, on the other hand, they are so lengthy, it means number of theoretical plates, as I said, would be very high, and hence resolution and column efficiency in capillary columns is going to be very high, but on the other side sample capacity in such columns would remain on the smaller side, right. So, it basically depends upon the choice or the final use for which you are using GC, that whether you would go for a packed column or capillary column. But having said that, I can also continue with this, that most of the columns used in contemporary gas chromatography are of the capillary kind. So, now coming to the second part of gas chromatography, it is about the sample injection, and as I told you, the constituents must be volatile, so that they become in their vapor forms as soon as an injection is made, so that a carrier gas can carry them effortlessly. So, they also must be present at an appropriate concentration, and then injecting the sample must not degrade the separation, which means that your analyte, your solutes should first of all be volatile, should have low boiling points, but at the same time they should not degrade within the temperature range applied in a gas chromatography, and that, as I told you, could stay somewhere in between, let us say 50 to 400 degrees Celsius. So, then the next question arises is, we could have a sample which, apart from containing volatile components, could also contain non-volatile components, right. That is very common. So, for that we need to do some pre-treatments, and using those pre-treatments we tend to separate volatile components from non-volatile components, and then the volatile ones are finally injected. So, this is pre-injection component of gas chromatography. I will not discuss this part in details, but I will just let you know what kind of methods are used for separation of volatile from non-volatile matrix. One is a simple liquid-liquid extraction, and this is something we have also discussed, I think, in the first or second lecture. Then there is this solid phase extraction which can be used. Some new methods like solid phase micro extraction or purge and trap and head spate sampling, all these methods are used to separate the volatile samples or concentrate or enrich volatile samples, and once done, this volatile sample, a plug of volatile sample, is injected in a gas chromatographic instrument. Now, the other thing about this is, I told you a solute should be present in enough concentration. When I say enough, it should not be very large, because if you happen to have a large concentration, one can overload the column and that would degrade the separation. On the other side, if concentration is small, that would mean that signal is not adequate and analysis would become difficult. So, again the point is, it is about a trade off. So, you should have just the right amount of sample which should be injected in a column. Now, coming to the injecting port or an injection port of a gas chromatograph. So, if one is talking about a packed column, injection is fairly simple. So, one needs a syringe, and that syringe is put through an injection port which consists of just a rubber septum, and one can add up to, let us say, 10 to 20 microliters of an injection. And then the injection port is generally heated or kept at around 50 degrees above that sample component which is having highest boiling point. So, that would mean that all the components, as soon as they enter this port, are vaporized, are in the vapor state, and those vapors are carried through this carrier gas to the column. Now, coming to the capillary columns, sample injection is not all so straightforward, and because of that there are three eminent ways in which injection is made in a capillary column. The first one is split injection, then splitless injection, and then there is an on column injection. Now, once I go to this split injection, I want you to understand why there is a need for some specific injection modules in capillary columns. Now, as I said, capillary columns, they can handle very small analytes, sometimes of the magnitude of, let us say, 0.1 microliters. So, your injection syringe is carrying a volume of 20 microliters, but your module, your column, can handle only 0.1 microliters. It means that you need to discard a lot of that sample before it goes into the column, right? And that is precisely what is done in a split injection mode. So, only a portion of sample injected is introduced inside the column, and as you could see, most of the column is actually ejected out of this, most of the sample is actually ejected out of this split vent, and the carrier gas takes only around 10% of the sample. So, it is used for concentrated samples, but it is also used in general. The other thing is that with this injection, isothermal elution can be performed. It can be used for both isothermal and gradient, and I will explain them later. The next one is about splitless injection mode. Splitless injection mode is generally tried on some trace analysis on solutes which are already present in very trace amounts. So, in this case, let us say your injection syringe, your analyte is in 20 microliters of the sample, but in that 20 microliters your trace analyte is there, let us say, in just 0.1 or 0.01%. So, you cannot afford to lose that 90 ml in a split mode, right. So, what happens in this case is, we allow most of the sample to actually go through this injection port, but what happens is, there is some pre-concentration at this site. So, during this pre-concentration, the those trace elements or trace analytes are concentrated, and then a temperature gradient is applied, and use of that temperature gradient would mean that those analytes would then start to be taken over in the column. So, it is used for dilute samples. I will not say it is really dilute samples, but samples containing analytes which are in trace amounts, or at least some analytes which are in trace amounts. Then it should not be used isothermally, as I told you that at this point we tend to gradually raise temperatures. So, it is not ideally suited for an isothermal elution. The other one, the last one in this capillary column, is an on column injection mode, and it happens not so commonly, but it happens in certain cases where the sample is very delicate and you cannot afford it to really go through that injection port. So, it is directly loaded onto the column, and this is the third one, a column injection mode. So, then having said that, the next thing is about the column's temperature, and it is very important in gas chromatography to maintain the temperatures of the column and to keep those temperatures very high. The optimum column temperature depends upon, as I said, depends upon boiling point of the sample. It also depends upon the degree of the separation required, right. There is generally two types of operations through which this temperature is applied. So, at this point I like to draw an analogy between this temperature gradient or applying of temperature in gas chromatography with the kind of mobile phases we used on the basis of polarity in other chromatographic techniques, and there is a relationship, there is a direct relationship. In gas chromatography you cannot change polarity of the mobile phase. So, instead of changing polarity of the mobile phase, you tend to change the temperature of the column, and it does the same effect, okay, which is done by changing polarity of the mobile phase. So, as I was mentioning, there are two types of operations involved. You could have isothermal programming, and one can also have gradient temperature programming, which are again similar to what we saw when we said isocratic elution and gradient elution in the previous lectures. So, what happens in isothermal programming? It is a method which would hold the column at the same temperature for the entire process, and in case of broad boiling range solutes, this is not the ideal way to go about, because it would result in very long retention times for the whole programming. So, then in that case we would certainly like to go for gradient temperature programming, which is generally routinely used in gas chromatography. So, in gradient temperature you start at low temperature, so that your low boiling solutes are separated first, and then you start to increase the temperature, so that your high boiling point solutes also start to come off the column with good resolution and within a good reasonable retention time. This brings me to the last part of gas chromatography, which is about detectors used in gas chromatography. A detector would certainly measure the solutes. There could be different types of detectors used in gas chromatography, and different detectors certainly use different types of selectivity. The characters which one would look in an ideal detector is they should have adequate sensitivity, high reliability, they should be non-destructive, should have good stability, should be responsive to all the solutes, and should have a linear response over a wide range of solute concentrations. Unfortunately, you would not find a single detector which would have all these characteristics. So, then you would use detectors based upon the kind of separation or the kind of solutes one is looking at. There are basically two types of detectors, one which are based on concentration. So, a signal is directly related to concentration of solute, for example, thermal conductivity detectors or TCDs, and electron capture detector or ECD, whereas the second ones in this line are mass flow dependent detectors, which means that signal is related to the rate at which the solute would enter the detector, and based upon this one can count this flame ionization detector, which is widely used in this. Apart from this, there are other spectroscopic detectors also used, especially the mass spectroscopic detector used in this gas chromatography too, and that is used quite often. So, and then there is this also nitrogen phosphorus detector, which is an example of mass flow detector. So, another thing is there are certain detectors which are called universal detectors, examples being these TCD and FIDs. And these universal detectors means they can be used for a wide range of solutes which are used in gas chromatography, and hence one could obviously pick them up for gas chromatography. So, then these are capable of measuring presence of almost all organic compounds and many inorganic compounds also. So, what happens is TCDs, for example, they are the earliest gas chromatographic detectors, and they work on basically they measure this change in thermal conductivity of a column effluent. So, what happens is in these cases where these TCD detectors are used, you generally have a reference carrier gas as helium, and helium being the most susceptible and would have high thermal conductivity gradient. So, as soon as an eluent, an analyte is coming out with helium, that thermal conductivity is disturbed, it becomes less, and that signal is actually caught and recorded. So, the other one is this linear dynamic range, a large one which is up to 10 raised to power 5, they are non-destructive. So, if you are using a non-destructive TCD detector, it means you can use it for preparative purposes, although I said you do not use GC for preparative generally. And then the sensitivity is not so high in comparison to other detectors we are going to use. So, there are pros and cons using this kind of detector. They are certainly cheaper than the other detectors we are going to see. The other one is flame ionization detector, which would measure the production of ions when a solute is burned in a flame. So, what happens is as soon as carrier gas comes in with solutes and those solutes are burned in a flame, they generate a lot of ions and electrons, and then you add a huge potential across, and then because of that potential you generally generate here a current, and that current is the one which is actually detected in flame ionization detector. So, then generation of ions is directly proportional to concentration of solute in this flame ionization detector. The features are that it also detects almost all organic compounds except carbonyl and carboxylic groups. So, it is an universal detector as already told. It is a destructive method. So, your compound is actually burnt. So, this detector cannot be used with a preparative GC, of course, and then the sensitivity in this case is higher than the case we saw previously. It has a wide dynamic range as well. And I also told you that apart from these, there are other detectors also, spectroscopic detectors one should mention, like mass spectroscopy certainly goes along very well with gas chromatography. So, what we had seen in this lecture is shown in this slide. We spoke about gas chromatography, we tried to define the term, and after that we looked into how and what shape of columns can we use. So, they could be packed or they could be capillary columns. We could also see the sampling and pre-treatment of sampling using all of these methods like liquid-liquid extraction, solid phase extraction, so on and so forth. And then we saw about the injectors, and we saw that injectors could be on column, could be simple ones or could be split or splitless ones used in capillary columns. And then finally, we moved to the detectors, and we figured out there were a lot of detectors which can be used with a gas chromatography based upon certain pros and cons, and depends upon a chromatographer's choice. One can pick a TCD or an FID or an NPD. This is nitrogen phosphorus detector, and as I said, spectroscopic detectors, mass spectroscopic detectors, and there are certain other detectors as well. So, with this I hope you would be able to understand this very important concept and very important class of chromatography, which was gas chromatography. Next time when we meet, we would learn about another very important chromatographic method, which is high performance liquid chromatography. With this, I thank you very much for your patience and being with me. Thank you.